So I'm happy to open this morning session of the last day of the meeting with our second keynote speaker, Knut Urban from Germany. Knut, I think that quite a few of you know him, but I will still say a few words. He will tell us about a lot of the work that he did concerning electron microscopy, but he really is one of the world's experts in the field. He has received numerous prizes for various aspects of his work. I will not name all of them, but just to name a few, the von Hippel Award from the Materials Research Society, the Honda Award, and of course most recently the Wolf Prize, which he came to accept in Israel about 2 years ago, if I'm not mistaken. But most important is that in the early 90s he did a lot of excellent work on quasicrystals. And so I've known him since 1995, I think, since I was still a student. And I can just attest that Knut is a great supporter of Israel, and he has a lot of friends in Israel, and I'm happy to be one of them. So please, Knut.
So thank you very much for this very generous and very nice introduction. It is, of course, a pleasure for me to be again a speaker on one of the scientific events organized by Tel Aviv University. And I shall talk about aberration-corrected electron microscopy today. As always, I think some of you have already heard my lectures. I just decided, nevertheless, since the audience is a young and exciting audience, but not always in the field I'm working in. So I have decided to talk again, as I did it before a number of times, on the background of this exciting picometer electron microscopy. As a matter of fact, the introduction of aberration-corrected electron microscopy about 15 years ago has triggered a sort of a quantum jump in electron optics, and we have a lot of new applications in various fields, which range from basic physics, material science, even to life sciences. In my opinion, however, I think that the cutting edge is represented by the fact that modern electron microscopy allows us to do material science in atomic dimensions. Actually, during this talk, we shall drive microscopy to the extreme. That means we want to do picometer electron microscopy, which means that we want to measure atomic positions or atomic displacements in the picometer range. And just to recall, a picometer is just 1/100th of the diameter of the smallest of all atoms, the hydrogen atom. Now, before we go into the story, let me add a brief personal comment. In the past 10 years or so, I have been invited to give dozens of seminars and invited talks on conferences on electron optics. And it is indeed a striking experience that the majority of my listeners, of my audience, come to my lectures with the very firm opinion that electron microscopy in atomic dimensions is nothing more than a continuation of light optics employing a radiation with a shorter wavelength. And this, if you allow me the word, simple-minded view is forming the background for the general ad hoc assumption that electron microscopy in atomic dimensions, just by pressing a button, so to speak, is able to obtain something like a projection of the atomic structure, of the atomic arrangement inside the highly magnified sample. And this view is, of course, inadequate. It's, in some cases, entirely wrong. It's wrong since the atomic dimensions, of course, are governed by quantum physics, and electron microscopy is no exception. And in reality, we are not imaging atoms directly. We are imaging Bloch states at best. We are imaging stationary states in a potential. And this means our major task is to learn from these Bloch states, from these stationary electron states, about the position of the atoms. So now let us start our story. As always, I start like this. We start from scratch. That means we are asking ourselves, how is an atomic image formed in the transmission electron microscope? And as a physicist, I start with a sum over delta functions which are centered at the atomic positions R sub I. These are the atomic positions. We want to measure these atomic positions. And we also are interested to measure, to learn about the type of atom which is sitting in a particular position. And in order to do this, we employ an electron wave field. And while this electron wave field passes through the specimen, it interacts with the atomic scattering potential V of R. V of R, and the information on the specimen is then contained in the wave function of the electrons in the moment where the electrons are leaving the specimen. And this so-called electron exit plane wave function is given here as a simple sum over Fourier components. These are essentially plane waves with an amplitude and a phase, and G is a reciprocal vector, which is also called a spatial frequency. It just characterizes the fineness of the detail a particular Fourier wave is describing. And it's this exit plane wave function and not the specimen itself, let alone the atomic structure. It's this exit plane wave function which is the object of our objective lens in the microscope. And when we have an ideal lens, the image intensity distribution is just the absolute square of this exit plane wave function. In reality, however, we have lens aberrations, and the physical effect of the lens aberrations is that these Fourier components here are multiplied by an additional phase factor. And the heart of this phase factor is the so-called aberration function. It describes the technical state of your electron optical instrument. There are about 15 terms here which have to be considered in modern ultra-high resolution electron microscopy. I have only written the most important ones for us here in the moment. And the first one is the so-called spherical aberration term. We have the spherical aberration parameter. We have the electron wavelength, and we have the spatial frequency. The second term is the so-called defocus term. When you defocus a lens, it has on the image the same effect as a lens aberration, and so we call it the defocus aberration. And you have here the defocus parameter, which describes the actual focal length in the moment with respect to some reference value, lambda, wavelength again, spatial frequency. And as a result of the multiplication of these amplitudes with this phase factor, of course, you get a modified intensity distribution in the image. So let us briefly recall what spherical aberration is. You want to image a point in the object into the Gaussian image plane, and the position of the image plane is given in ideal Gaussian optics by the ray paths of the paraxial rays which are making a small angle with the optical axis. And spherical aberration means that when you have a wide angle a bundle of electrons, that these pass the lens at the periphery and they come to a focus much ahead of the Gaussian image plane, and as a result of that you do not image the point into a corresponding point here, but rather into an aberration disk, which is given by this so-called point spread function, which is the derivative of this aberration function, which we just got to know a minute ago. So we know since the pioneering work of Ernst Abbe in the 1870s that we can correct the spherical aberration of this converging lens by combining it into a system with a second lens, a diverging lens, and then the focal length becomes everywhere the same. Unfortunately, this type of technique cannot be used easily or directly in electron optics. The reason is that magnetic fields have to obey Gauss' law, which means nothing else than that the magnetic field lines have to be closed. And with field lines which are closed, you can only construct converging lenses. So we could show in the 90s, that means 70 years after the discovery of the invention of the electron microscope, that you can nevertheless build something which is the equivalent to a diverging lens. And we exploit for this a second order effect of multipole lenses, in this case hexapole lenses. And I just summarize the action of this by showing you schematically the ray path. We come in with a parallel bundle of electrons and they leave as a diverging bundle, so that this system acts as if we would have a real diverging lens. And this allows us now to correct spherical aberration in electron optics. And the 1997 prototype, which we built, has become, so to say, the mother of a new generation of electron microscopes. And this is the newest of them all, the FAI CEOS Pico instrument, installed nearly 2 years ago now in Jülich. It has a Rayleigh resolution of 50 picometers and allows a precision of 1 picometer. So how is it possible that we carry out picometer microscopy with an instrument which has 50 picometers resolution? And for this we have to separate, we have to look in detail into what is resolution and what is precision. So according to the Rayleigh criterion, I have to apologize for the projection. The projector just bleaches out everything, so the contrast goes down, but I think at least I can describe what I'm talking about. So when we have two overlapping contrast maxima, in this case of atoms, then the resolution is defined by the minimum distance with which we still can see these two contrasts separated. And this resolution is about 50 picometers today. Now, as soon as we have separated these atomic contrasts, because we have bought such an expensive instrument, that means they now are optically separated, then resolution is no longer important. What then counts is precision, and it's the precision with which we can localize the maximum of this contrast figure. So, and this maximum, this depends on the signal-to-noise ratio. This precision is nearly 2 orders of magnitude higher than the resolution. And this allows us to do picometer microscopy in that sense that we can measure, for instance, the distance between these two maxima to 1 or 2 or 3 picometers. And this is the background of what I'm talking today. So now we have bought the instrument, we have the optical quality. The question is this all we need to look what's up in picometer dimensions, to study things in picometer dimensions? And the answer, of course, is no, because we have only dealt with one of the ingredients of microscopy. The first one is optics. That's what we have done. And the second one is the reaction of the wave field, the electron wave field, to the atoms. It's the question, how can atoms produce contrast in such an instrument? And for this, we just go back to my first slides, and we saw that while we send this wave through the crystal, it interacts with the atomic scattering potential. This interaction has to be described by a Schrödinger equation. Actually, it's a Dirac equation because we have relativistic electrons, but it turns out that you can simplify this equation so it adopts a Schrödinger form with relativistically corrected mass, wavelengths, and kinetic energy. So the solution of the Schrödinger equation are Bloch states at best, or in any case something like a Bloch state, very generally a stationary electron state of electron waves going through such a specimen. And the wave field here is mathematically complex. That means it's described by amplitude and phase. So when we want to exploit our instrument to the limits to measure what we can measure, then of course we have to care about amplitude and phase and measure this. Nevertheless, you can intuitively understand quite well what the amplitude and the phase part means, and this is what I want to visualize for you now. We first deal with the amplitude part. The amplitude part can classically be quite well understood. Assume that we have a specimen surface. Here we put on a parallel electron beam. The thickness increases in this direction of your specimen. And then the electrons get accelerated towards the positive atomic strings. And they get localized there in certain thickness values, certain depth values, and then they fan out again because the core of the atoms is so small they never meet the atomic core directly. And then that's what you get. You get an oscillatory motion of the electrons. That's the Bloch states. We are so often learning about Bloch states in our lectures at university, but this is the behavior of a Bloch states. Now, the solutions of the Schrödinger equation, of course, depend on the potential. So when I have two types of atoms, a high nuclear charge material and a low nuclear charge material, they behave differently. So these electrons here take long time to get concentrated at the atomic positions, while these here are oscillating very fast. And this has the consequence that when you change the thickness in the sample, and you have the same structure, the contrast which you are observing is different because it depends on the nuclear charge of the atoms. That means the same structure gives you different images depending on the thickness and the nuclear charge of your atoms. And this is shown in this video here where I have now plotted the electron current density as a function of thickness of your sample. That means we just increase the thickness now in the video, and we just look how the electron current density develops. And this is the primary object. This is the object of the objective lens of the microscope. And here you see now, here we have strontium, we have titanium and oxygen. You see how with increasing depth, the image varies dramatically. And you see also that there are certain depth values where the strontium as the heaviest atom is not visible. It's hardly giving any contrast, while the other two types of atoms give very strong contrast. So this is not that we are unable to do proper microscopy or so. That's the physics. There are certain depth values where strontium cannot be seen. Okay, but this, as you will see, is not an obstacle. But I just do this again, and you see also how slowly the oxygen develops here. This is the oxygen, very slow behavior. You see, while the strontium just oscillates quickly with increasing depths of your specimen. So that's the behavior of a specimen in quantum mechanical dimensions. To deal with phase is not so straightforward. You know that phases cannot be registered directly. That means you have to convert phase information first into amplitude information. And this resembles very much the Zernike case in biological phase contrast microscopy. And in the Zernike microscopy, you just take your primary beam in the microscope and the diffracted beams, and you shift the phase between the primary beam and the diffracted beams, ideally by 90 degrees, by the famous Zernike phase plate. We don't have Zernike phase plates in electron optics, and therefore we have to look for a substitute. We have to look for something which shifts the phase between the incident beam and the diffracted beams. And we have something like this. It's this awkward aberration function. This aberration function has also a positive effect because it allows us, this is just the index, so to say, of the beams. These are the diffracted beams. So we can shift the phase between the incident beam and the diffracted beams by applying the aberration function. And this means that we do not really focus our object entirely. We do not work at ideal focus. We do on purpose defocus our object a slight little bit. By a given amount, we have to defocus. Otherwise, we have no access to the phase of the signal. And we also found out, I just discovered it's already 10 years ago, that we found out it's also useful in an aberration correcting microscope not to correct the aberrations entirely. Somebody who is not familiar with this would find this very strange, that you have a means to correct the spherical aberration of your instrument and you don't do it at purpose. We always maintain about 5% of the original spherical aberration in order to get good contrast. So in atomic resolution, your objective lens has two functions. The first one is to image. This is the normal one. And then the second one is it has the duty to convert phase information into amplitude information. And that's done by defocusing and by some small spherical aberration value. So you see that's quite strange what you are doing in atomic dimensions, but that's we want to get access to the physics in these dimensions. Now you see the whole thing is an intricate problem, and you also understand by now, I think, that you cannot simply look at the images and interpret them as it's normal. That means the image interpretation becomes an interesting point now. And we, of course, know that in normal light optical vision, in photography, light microscopy or so, your brain automatically interprets your images. For instance, here we have a landscape, we take a photo, and this is the imaging process. Now your brain just inverts the imaging process. It goes from the image to the structure automatically. You cannot help it. You do it automatically, that the brain just constructs a mental image in your brain out of this. So we have also brains. So also here, a brain comes in. So take Feynman's brain, or Schrödinger's, or Heisenberg's. They have created quantum mechanics, but nevertheless, their brains do not understand intuitively quantum mechanics. So we have to find a brain which understands quantum mechanics. And this is the computer. We can program, of course, the computer that it follows the quantum physical laws. That means the understanding of image formation, in our case, has to be done by the computer. That means we now have to invert the imaging process as the brain did it here. We have to invert this in the computer. So that's how we get access to the contents of our images. So that's what the computer does. It does it in two steps. The first step is to go from images to the exit plane wave function. It's the first step. That's done with a very established technique, the so-called focal series reconstruction. That means we take a series of images. In between, we change the focus of the lens by a given amount. And this means that we are probing, in a way, the phase shift behavior of the lens. And this has very much in common with interferometric imaging. And we now plug these images into the computer, and it gives you then the exit plane wave function when everything is done right. So now we still have a second step to be carried out, and this is to conclude from the exit plane wave function back to the structure. And this unfortunately cannot be done in a direct backward calculation. We have to do a forward calculation. For this, we construct a first guess model of our atomic arrangement, and then we solve the Schrödinger equation, try to predict this, and then we just vary the atomic positions until we get a good fit. That's a quite involved procedure, because when you want to do picometer microscopy, you have to adjust the atomic positions of some 10 up to 100 atoms to a picometer. And there is another point which we now have to mention, and this is that the Schrödinger equation, everybody knows this here, the Schrödinger equation, the solutions of the Schrödinger equations depend on the boundary conditions. So we have to know what the boundary conditions are. And of course, after the video, you know that one of the key boundary conditions is the thickness of the sample. But in quantum mechanical dimensions, you cannot measure the thickness of your sample. So a priori, the thickness of your sample is not known. So it can only be found by a scattering experiment. And the scattering experiment is your imaging process itself. So we have to take the thickness of the sample as a free parameter in this fitting process. And the same holds for the angle of incidence of the electrons. No way to get access to the angle of incidence of electrons in atomic dimensions. So we have these two parameters, and we have some more. So in the end, when you have finished with this, it's clear to you now that electron microscopy in atomic dimensions does not produce images. It produces a model of your sample in the computer. There, everything is done right. So we have, as a result, we have the model, and now I give lectures to you, and so I would, you know, if I would be a simple-minded person, I would give you a table of atomic positions, and that's quite boring. X-ray people publish long tables of, and so on. But we have an imaging instrument, so you expect an image. So what I can do for you is I just take the image series, which I have taken before, and I now select on purpose. I select the image which fits best to our model and to your intuition. Because your intuition always assumes that you look through something, you have a projection. So I count on this intuition and give you the image which you want to see. And this is actually the reason why such an auditorium and even larger ones, hundreds of people, come into the lecture with the impression that we just press a button and then we have the projection of the atomic structure in quantum mechanical dimensions. So for discussing things, for publishing papers, for talking to you, it's fine. But don't take now a measurement instrument and measure the atomic positions there. This looks so wonderful as strontium titanate, so we should be happy with this. But now we look a little bit more closely. That means we magnify, and now I point to this oxygen atom here. And you see the oxygen should be just in the middle between two titanium atoms. It's not, it's shifted towards one of these titanium atoms. In addition, we look at the titanium. Titanium should be aligned with these two strontium atoms. It's not. Titanium is shifted. And the reason behind all this is, the shift is substantial, 30 picometer. You cannot just say, I neglect this. You have a technique which allows you to measure 1 picometer. So you should not settle with 30 picometers misplacing of atoms. And the reason behind this is specimen tilt. The mechanical adjustment possibilities you have in such a modern optical instrument are still Stone Age, or Metal Age, let's say it like this. So that means the ability to align your specimen is not good enough to align your sample mechanically parallel to the electron beam. So in general, all atomic resolution electron micrographs are tilted micrographs. And of course, you are not interested in a tilted image of your sample. So you can say, okay, this is geometry. I just apply to each of these atomic maxima a geometrical factor, and then everything is fine. It's not, because the background of this is something else. Bloch states in a potential react differently to tilt, depending on the nuclear charge. That means when I calculate the solution of the Schrödinger equation for a tilted potential for oxygen, this gives me different tilting effects compared to the titanium. So this is the background of this. You cannot treat tilt in quantum mechanical dimensions simply by a geometrical factor. You have to treat the Bloch situation. You have to treat the wave equation for this. And when we do all this computer fit, this type of tilt effects is eliminated. That means it's taken care of. That means when you want to do quantitative measurements, better do it in your computer model, because there everything is fine. Okay, so now we have everything together to talk about a few relatively simple examples. And the first one is a classical example which I put always into these lectures, and this is the 90-degree tilt grain boundary in yttrium-bound copper oxide. I'm running a superconductivity group since more than 20 years now, and at the invention of the high temperature or discovery of high temperature superconductivity, we immediately started to work on Josephson effects in single crystals of yttrium-bound copper oxide, and we are interested to produce squids to measure very low flux densities, and I will come back to this. And we are accompanying our layer deposition work with this atomic resolution electron microscopy. And here you see the 90-degree tilt boundary in the framework, what I have said, in the framework of what I have said before. That means we have the unit cell of yttrium-bound copper oxide. Now we go across the boundary, and it just tilts by 90 degrees, and we see in quotation marks all the individual atoms. This is the perovskitic unit cell of yttrium-bound copper oxide, and we see the copper atoms. We see the body-centered barium, yttrium, and arium atoms, and we also see the oxygens. So we can now return back to our grain boundary and hope that we can measure all the necessary effects there. So the first one is you have a look at the copper pair here, which is close to the yttrium atom. Yttrium is a relatively small atom. And then we have another copper atom pair, which is close to the barium. Barium is a fat atom, so it presses the lattice apart, and obviously you can see this. You see directly in the image. Then we have a second effect. Every third copper atom here in the boundary shows a weak contrast, and you also, I think, will be able to see that there is another weak contrast here. These are the oxygen atoms which are relaxing towards the copper atom, and this tells us that the boundary is reconstructed, as we call it, and this is shown in this model here. This is the close pair close to the yttrium, and this is the wider atom pair. So the separation here, this is 44 picometers smaller than this distance here. Also, we see that obviously 3 upright standing unit cells down here do not give the dimension of a lying unit cell, and you get a misfit of 22 picometers. And this misfit leads to a disorder effect, including the oxygen. I cannot go into that. And you can measure this directly to 22 picometers. So we can construct displacement maps around the boundary. This is the boundary, and we see that in the boundary, the copper, the oxygen relaxes to the copper by 6 picometers. We can measure 6 picometers, and up here we have the yttrium. It is dragged into the boundary by 9 picometers, while the fat barium is just moved out by 11 picometers. So these are enormously small numbers. I think even the most futuristic electron microscopists a few years ago would not have even dared to dream of small numbers like this. So just for illustration, the supercurrents are flowing like this, and in between we have the Josephson weak link. We are building squids out of that. That means we need 2 of these Josephson junctions. We are packaging that into a sensor. And as you see here, we can measure magnetic fluxes down to 3 femtotesla. That's 6 orders of magnitude smaller than the Earth's magnetic field. With these sensors, we sell them to our former competitor in San Diego, and they distribute it worldwide. And I think it's a wonderful case of atomic resolution work than finding its application in the macroscopic world. Here we mount this sensor to a scanning device, and in collaboration with a clinic in Berlin specializing on heart problems, we now can measure the magnetic field above the heart at various phases of the heartbeat cycle. So my next example is ferroelectric domain walls in PZT. PZT means lead zirconate titanate. It's in the meantime technical ferroelectric, which is used for many applications. And just to start with, let us briefly recall what ferroelectricity means. We go to a very high temperature, and then the lattice of PZT is highly symmetric. It's centrosymmetric. That means the center of the cation charges and of the negative oxygen charges, they just coincide. There is no magnetic moment on the unit cell level under these conditions. Now we reduce the temperature below the critical Curie temperature, and this is accompanied by a phase transformation. That means the lattice becomes elongated and it loses its centrosymmetry, and now the charges of the ions and the cations do no longer coincide. And this means that we have an electric dipole formed on the unit cell level. Every unit cell carries an electric dipole, and this even without a field, and this means ferroelectricity. So we have studied films like this, deposited by pulsed laser deposition, and we just can localize the position here of the lead atoms, the zirconium, titanium, and also of the oxygen. So the oxygen is displaced out of the zirconium, titanium atom row, and this tells you that the material is polarized, and we can measure now these atomic shifts, and from this we can derive the strength of the electric dipole. On the unit cell level, we do the same here, and we find the oxygen is displaced downward here. We again measure this, and we find that the dipole is now pointing in the opposite direction, and we can, of course, calculate from the atomic shifts, we can, of course, calculate the electric moment. So in between must be a domain wall, 180-degree domain wall, and we are just looking here at a sketch of the domain wall in various places. We have domain walls, these are the inclined ones, where the dipoles meet head to tail. That means they compensate their charge. That means this should be an uncharged domain wall. But in these flat areas here, we get a collision between the dipoles, and they do not compensate the fields. The opposite is the case. They enhance their electric fields. These walls should be charged. Now, an important characterization parameter of these walls, of course, is their width. And we measure these now in atomic dimensions. And you see that the oxygen is going down here, it's going up here. That means the change is within one projected unit cell. This is a 110 view. And that's the smallest possible distance. And this is corroborated by the quantitative measurements. Now we go to the charge domain wall. We measure in this and in this direction. And we find this result. I have just plotted here, for instance, with the blue symbols, the shifts of the oxygen atoms, which are an indication of the polarization. And we find that now the width is 10 unit cells. And this is just the way how nature reduces the energy of the system. When you just pull this apart, the electric field goes down and the field energy as well. So this figure here is of quite a paradigmatic importance, because here we have calculated the macroscopic polarization. That means the polarization which you would measure in a laboratory environment. And this polarization is calculated on the basis of atomic data. So in a sense, you can say this fulfills an old dream of material science, that you calculate macroscopic properties which determine your life from atomic dimensions. So this is a very brief glance of very recent work. We are interested here in the interface between lanthanum aluminate and strontium titanate. Both are isolators. But about 10 years ago, people have found, or Thoma and Wang have found, that when you construct an interface between strontium titanate, for instance, as a substrate, and lanthanum aluminate on top of strontium titanate, you get an interface which is a metallic conductor. So people have done a lot of work. There are hundreds of publications on this effect, but still there is no full agreement what is behind this. And part of the reasons is that people were not able to measure the properties on the atomic level. So we have recently done this type of experiment. That means we have investigated a single layer of lanthanum aluminate, a single unit cell layer on strontium titanate. So we have a strontium titanate substrate, and this we call a capping layer of strontium titanate. In between, we have the lanthanum aluminate. So that's the one of the micrographs we can take under atomic resolution, and the lanthanum aluminate unit cell is just here. Very difficult to see, but you can find it. So in this case, we exploit an advantage of this sample, because here we have perfect strontium titanate. We know the structure, and so there is no problem to calibrate the thickness, the angle of incidence, and that means to find the imaging conditions in strontium titanate far away from the problematic area. And here I should briefly mention that we need this area also for something else. When you adjust your microscope, maybe at 8 o'clock in the morning, and you take such images at 8:30, it's quite likely that the correction values which you have adjusted, they have shifted away. So your correction is not what it should be. So that's the reality at the borderline of electron microscopy, the forefront of electron microscopy. Stability becomes an issue. So you have new aberrations coming in. And these residual aberrations can be corrected when you do experiments in this perfect area. That means we can numerically, a posteriori, so to say, we can correct these aberrations. That's one of the difficult parts of this type of work. And with this, then we go to the problematic area. So this simply should illustrate to you that we can get wonderful fits. This is the full symbol is the computer fit and the empty symbol is the experimental results. So sometimes you cannot even distinguish these. So we can nowadays get essentially 100% fit on the absolute scale of the intensity and the contrast. So now to the results. This is the concentration measurement. That means we have essentially a means to measure concentration on the atomic level. And so this is the capping layer area, and this is the substrate area. So the whole thing is tilted by 90 degrees. So this should be lanthanum, a lanthanum layer. And what you find is that you do not have 100% lanthanum, but 55%. The rest, 45%, is strontium. So you have a tremendous intermixing. And this should be a pure aluminium layer here. And what you have is a mixture between aluminium and titanium, only 35% aluminium, and the rest is titanium. And this here should be a pure titanium layer, because it's the last layer of your strontium titanate substrate, should be 100% titanium. What is the reality is that you have 75% titanium and 25% aluminium due to this intermixing. And so we find here the background of the conductivity, lanthan doping of strontium titanate, that's known from different experiments, leads to conductivity, and also the oxygen vacancies. You see oxygen goes down here in concentration, and oxygen vacancies introduce conductivity into strontium titanate. I have no time to go into the atomic position measurements. I just want to go to the final experiments I want to show to you. It's from the collaboration with Jing Chu's group at the National Center for Electron Microscopy in Beijing, where I'm a guest professor. And this study is into the surface structure of cobalt spinel. We are interested to look into these oxide particles with respect to their properties as a possible catalyst. And so this cobalt spinel is a 3x2 spinel. That means cobalt is 3-valent and 2-valent in this case. And the unit cell is quite large. It contains 8 formular units, 56 atoms. And now we are interested to learn about the 1-1-1 terminations. And now we draw a line towards, along 1-1-1. And we just look into the possibility to terminate this. We just cut through this. And there are various terminations, 6 types. And these surfaces can be polarized, that means charged, or not polarized. And people have speculated a lot about the properties of these surfaces. So we now approach this problem doing this atomic resolution electron microscopy. And this is now a 1-1-1 surface in cross-section. And we first look at the outermost layer here. And we have here a pair of cobalt and oxygen. And we compare this pair with a pair more far away from the surface. You immediately see the buckling angle here has changed, and also the distance. The pair is now 84 picometers apart, and in the bulk you have 110 picometers. The investigation shows that the outermost layers here are shrinking by 50%. It's unbelievable. Sven Hofmüller said that's impossible. So nevertheless, it's there, and that means there is really a lot of physics going on out there. And this physics can be described by density functional ab initio calculations, and the results fit very well to the experimental results, but also to lead experiments. And the density function calculations can show us what is the physics behind this reconstruction of the surface. And we get, for instance, the result that the cobalt at the outer layer here is in a tetrahedral coordination. That means it must be two-valent cobalt. Then we have an oxygen layer, And the next cobalt layer is in the octahedral coordination, threefold cobalt, and so on. We can find these things quite nicely. So the DFT calculations minimize the Gibbs free energy, and they do it including the charge. That means from the DFT calculations, we should also be able to learn something about whether such a surface is charged or not. And when we just do a primitive counting of charges, then we come to the result that this should be negatively charged. But that's not the whole story. It's more complicated. So the DFT calculations give us access to what is called the Bartle charges. And here we learn that close to the surface, negative charge is moved away into the interior of the sample. Even oxygen loses charge at the outer surface layers. That means the result is that the specimen the surface is neutral. And I have put this work at the end of this talk because it shows the tendency today that the groups working optically in the picometer dimensions, they combine their work with DFT calculations. That means these two techniques are meeting now in dimensions where the physics happens. So these picometer dimensions is where the physics happens. And I think this demonstrates that electron microscopy has emancipated from a structure-oriented tool to a high-precision physical measurement instrument. Thank you.
Thank you very much. We have a few minutes for questions. Yes, please.
Could you, in this resolution, check also charge transfer complexes at all, or?
I think with the people are trying this and have tried it but you have to do this with the DFT calculations, because we, by the optical means, phase shifts, amplitudes, and so on, we cannot go close enough to this. But people have studied this already. As long as the charge transfer has an effect on the atomic positions, then you can see it. Yeah.
I have two questions both of them related to the thickness of the sample. In one part, you showed columns where you have a mixture of two atoms, like aluminum, titanium, or zirconium, titanium.
Yeah.
So what is the error bar there, and can you go down to a single atom replacement? And the other question is, I mean, those samples you didn't mention, but the samples are quite difficult to prepare, right? They are about a few nanometers thick, and they need to be fairly uniform. What's the influence of creating a surface on both sides of the sample? And often it is done quite energetically, right? So
Yeah. I think the thickness of the sample has to be such that I think you can, when you have about 15 to 20% of the atoms replaced at this charge numbers we are dealing with, then you can see it. We have done numerical calculations. That means to see a single atom in the moment is not possible. We are in the moment in the mid of work where Junlin Jia, who did much of this work, claimed to me recently that he can see a single atom. But in any case, that's not an oxygen column. It has to be a strontium or a barium column. So it's quite sensitive, because we have nowadays the means to do calculations on an absolute scale. And since you have experience in this field, we have dealt with the stops factor, because the stops factor in the past has essentially always led to the situation where you could only do relative intensity calculations. But now I think we know what the stops factor actually is, and so we can make proper measurements and then do our calculation on an absolute scale, and then probably you can go to one atom. So the other question, the second question, was specimen preparation. I think the specimen preparation nowadays is not really a problem. To prepare samples with a nanometer or two or so thick is not really a problem. But this does not mean that you do it today for tomorrow's electron microscopy session. Sometimes it takes a week until we have the proper specimen dimensions and orientations and surface qualities. We have not talked here about the surface qualities. I think, you see, there are not too many people who carry out picometer microscopy. Especially, I think there is in the meantime no group in US anymore doing this, because it does not fit to the modus, the rhythm of progress in a laboratory where you have to fulfill exotic time requirements. It takes time. It takes about 3/4 of a year to train a student to do this type of work. And you know, at university, then he leaves, or she leaves, and then you start to invest again. We can afford to train people and keep them for some time. So that's, we talked this morning at breakfast about persistence. And I think, you know, this is science. And science asks for another rhythm than the funding agencies. And there you can learn the preparation, you can learn how to do this. The error bars have been calculated, you see error bars. So we do normally a Gaussian regression fit, and so we know that the error bars are 90% confidence level and all this.
Yes, about the yttrium, barium, copper, oxygen junctions, Josephson junctions. Can you tell us how the TEM work helped you optimize the junctions, or is it just for understanding the mechanism of the Josephson junction?
I have to say in the beginning, because you see, the strange thing is I have started as an electron microscopy institute in Jülich more than 20 years ago. And in the meantime, till today, we are holding the record of squeeze sensitivity. So, you know, I'm not a priori a superconductivity man, but what we did is we are depositing our films using sputtering techniques, which are much more careful compared to a laser deposition technique, which we also do, as you have seen. But we have, in the beginning, we have combined the electron microscopy high resolution group, led at that time by Junlin Jha, with the people who did the layer deposition. And there we found out the parameters which we had to optimize to get these wonderful junctions. So that's a direct interplay of atomic resolution with layer deposition. But what really helps is the sputter deposition, because this gives you very well-defined layers.
The second question about the lanthanum aluminate strontium titanate interface. Did you try to measure more than one unit cell? Because usually people say that this strontium lanthanum intermixing occupies about 1 to 2 unit cells, and conductivity appears only above 5 unit cells.
That's correct. I think the point is, of course, we measure. This is absolutely right. We have effects of intermixing going to about 3-4 unit cells. It's not symmetric in the capping layer compared to the substrate layer. But I think it's not really shown that the conductivity effect is just concentrated to one atomic layer. So I think the best work that has been done in my opinion, is high-resolution X-ray scattering work or neutron scattering work. And there, the resolution is not a single layer. So I think that's not an objection. But I couldn't say everything here, because when you replace 4-valent titanium with 3-valent aluminum, you just get a charge compensation effect. So that means it's going into the wrong direction. In addition, I couldn't show this tetrahedron motion in the upper part of my figure here. We also found what nobody else has found before, that the oxygen in the first layers around the lanthanol aluminide layer, they are relaxing towards the interface. So you get a dipole formation in the interface, which partly screens the charges. And this also is going against this conductivity effect. So the whole thing is a sort of an intricate problem. So I see mechanisms, I see evidence for mechanisms, but in the end, the overall net result, I cannot tell.
So maybe one or two more quick questions and we have to move on.
Hi, it was a wonderful talk. Hi. What about softer materials? Why can't we have picometer resolution on softer materials and glassy materials? I mean, obviously it will be fantastic to have it for biological samples and so on. So that's maybe like a very general question.
Yeah, that's right. So I think that the general problem remains with electron microscopy, that you have radiolysis in organic materials, and you get radiation damage. And the radiation damage comes in because you need a certain minimum dose. That means electrons per square unit, square angstrom, to get picometer precision, because it's a signal-to-noise ratio which counts. That means when you go to smaller and smaller dimensions, the dose you have to apply increases. So far, the situation is this, that the resolution for biological materials is limited, say, to a few angstrom or nanometers.
What about glassy materials? I mean, glassy materials can be out of silicon, right? I mean, it's not a...
Right. So this was the organic materials part, because this but is this, that people have investigated organic materials at lower and lower electron energy. And it turns out that when you go to lower electron energy, then you gain in the applicable resolution. And this this is a development going on in the moment, that you now go to lower electron energies. When we go to amorphous materials, we of course have the advantage that we can when you normally have a microscope with spherical aberration, this spherical aberration always leads to this point spread. The point is just expanded into something else. We call this delocalization. So when you have a microscope with spherical aberration correction, delocalization goes away. And this opens up the way to investigate glassy materials. And when you are familiar with the field, there is always this intermediate field. In silicon, for instance, you have evidence that there is a tetrahedral coordination. But then you go, say, to the range of 2 tetrahedral diameters, 2 larger diameters. And there you can do scattering experiments where people claim, I have not seen results yet, that they have access to a size range which was not accessible before. So in the moment, everything I'm talking about is crystalline materials. And maybe in a sense it's easier there, but that's the state of this.
Maybe I'll ask Uwe to set up this computer. So
Okay. So you said the resolution is now 50 picometer. This is still about probably 20 times more than the wavelength.
Yeah.
So what is limiting now the resolution, and what is your prospect? How low can we get?
There are various factors of of course, it's chromatic aberration, which is limiting the resolution. And in the Pico instrument, we also have a chromatic corrector, and the Berkeley team instrument has also a chromatic corrector. It turns out in practice that we so far have not reached a chromatic correction which would really increase the resolution. And there will be a paper in PRL next month. And the reason for this is noise. That means as soon as the beam passes via metal, any type of metal, the electron motion in the metal does not fully cancel out. It just, at the time when the electron flies by these metal walls, the statistical average is not felt by the electron. It feels the real field by the moving electrons. So it's a mini effect, but we are at the borderline of everything. And so far, the chromatic correction has not helped us. In addition, we have coherence effects, which also limit the resolution, and mechanical instabilities. Part of the stops factor comes from this. So we have both in TEM and STEM, we have a factor which is a vibration of about 20 picometers, 15 to 20 picometers, which is instrumental instabilities, soil vibrations, and whatever. So you're right, we still have some way to go.
So, Knut, thank you very much. And there's a souvenir here for you from Tel Aviv University.
Aha, thank you very much.
From the organizers of the conference, and just the microphone, please.
Mm-hmm.